Dr Gurupatham from Kennesaw State University, and my partners who worked on this project are Carson Wiles and Naveed Yespahani. So the title of the presentation is Thermal Properties of Clove Seeds. So this is how I have arranged my presentation. So initially I will give some introduction on the research work and the research goal, and I will explain the experimental details along with the setup details. Then I will discuss the results that we obtained from the experiment. Conclusion will follow. I will also mention about the future work. So clove, the botanical name is Curcuma longa, may be considered as the best of all the known antioxidants, and the medicinal properties of clove seeds are very significant, and it has been a home remedy for curing several ailments and diseases. In pretty much in Indian families, this is inevitable in the kitchen. So the knowledge of the thermal properties of clove seed is essential for the design and analysis of its processing and the processing equipment with respect to heat transport. So our research goal is measuring thermal conductivity, specific heat and thermal diffusivity of the clove seed experimentally using the transient hard bridge method. We actually used two experimental setups. The first setup is for measuring the thermal properties of the clove seed using transient hard bridge. As we see here, so this is the transient hard bridge and the sample holder. It's like sandwich arrangement. So the sample can be gripped between these two holders, and by tightening this nut we can apply some pressure, very gentle pressure, and this is the sensor from which heat is transferred to the sample, and all the experimental results are captured in this laptop. And so this is experimental setup 2. It was used for validating the specific heat of the clove seed with the hard bridge method. So this is actually a conversion of 0.7 liter thermoflask into a calorimeter. So basically we drilled a hole and we inserted a thermocouple. So the approach is, in the setup 1, that is using the hard bridge method, a strip-shaped conductor is used as a heat source, and a temperature sensor is embedded between two pieces of the sample holder. The strip emits a constant heat flow during the measurement, which causes the temperature to rise. The temperature rise over time corresponds to the thermal transport properties of the sample. The additional temperature sensor in the setup is generating a differential signal, which is a time invariant measure of the thermal conductivity of the material under test. This signal is practically unaffected by homogeneous, isothermal, adiabatic, and the convective boundary conditions. So the experiment was performed by connecting the probe to the transient hard bridge and then connecting to the computer program. The program allows for user inputs. Through trial and error, the best setup was found to be 39 microampere, milliampere measuring current, and it was passed for less than 10 seconds. The whole clove seeds, which were chosen damage-free from a local Indian grocery store were piled up onto the measuring bed and clamped with a prop in between the sample so that the heat can be generated through the sample. The clamp needs to apply a slight amount of pressure onto the closed hits so that it does not puncture the sensor. The experiment was repeated several times to verify the repeatability of the outputs obtained from the experiment. The setup 2, which was used to measure the specific heat. So this method was developed by Hong and Hayakaman and modified by Mercalli and others. So it's basically an insulated stainless steel double wall of 0.7 liter thermal flask, which was modified into a calorimeter. The thermocouple which was used was type K, which was inserted at the center of the flask. So water was considered as the reference liquid, and 200 grams of it was weighed and placed inside the calorimeter at 70 degrees Celsius. The system was closed and placed on a shaker for 20 minutes to obtain a uniform temperature between the water and the calorimeter. Approximately 20 grams of sample close was kept in an aluminum container which has a dimension of 5 cm diameter and height of 3 cm, and placed inside the calorimeter at an initial temperature of 67 degrees Celsius with an indirect contact with the reference liquid, that is water. The thermocouple type K was inserted at the center to measure the temperature of the liquid inside the thermos. As I mentioned before, water was considered as the reference liquid, and 200 grams of it was weighed and placed inside the calorimeter at 70 degrees Celsius. The system was closed and placed on a shaker for 20 minutes to obtain a uniform temperature between the water and the calorimeter liquid. The system was maintained with a constant agitation until reaching a final equilibrium temperature. An energy balance based on the law of conservation of energy allowed calculating the specific heat capacity of the sample. So basically the initial calorimeter heat and the water will be equal to final heat of the calorimeter water, and this heat loss rate time times this is the time required, equilibrium time required for the sample to reach an equilibrium temperature with the calorimeter. And so using Q is equal to mCp delta T, we can find out the specific heat of the sample. So you can see that this Hk, basically all this heat is expanded with this corresponding mass times specific heat times temperature difference, and this is Hk, which is the heat capacity of the calorimeter itself. So we have a separate procedure for calculating that. While measuring heat capacity of the calorimeter, approximately 200 grams of water at 60 degrees Celsius, which is reference liquid, was weighed and placed inside the calorimeter. About 100 grams of distilled water at room temperature was weighed and its initial temperature was measured. The sample water was poured inside the calorimeter in direct contact with the reference water. The system was immediately closed and kept in the shaker for constant agitation until reaching equilibrium temperature. To measure the heat loss to surroundings, the system was left in the shaker for approximately 60 minutes, and from the slope of the linear portion of the temperature versus time graph, the heat loss rate was obtained and used in this expression. So basically what we are doing here is we know the specific heat of the sample, which is distilled water from the literature, and we are calculating the specific heat of the distilled water to validate its value from the literature. And in this process, we are also calculating the heat capacity of the calorimeter, and we are taking this value back to plug in the previous expression which I showed before. So, results and discussion. The thermal properties of the flow sheet were measured using the transient hard bridge method. The thermal conductivity turns out to be 0.055 watt per meter Kelvin. Specific heat to be 2.823 kilojoule per kg Kelvin, and the thermal diffusivity is to be 2.8724 millimeter square per second. A linear relationship between the dependent variable of specific heat and the independent variables of moisture content and temperature from the multiple regression analysis. It's from the literature. The following expression is obtained for the comparison, and so we have the consolidated results here. So from hard bridge method, thermal conductivity, specific heat, and thermal diffusivity are shown here, which I mentioned just before, and the same is compared with especially the specific heat is compared with calorimeter method and linear relationship method. So it turns out to be 2.8029 when we measured through calorimeter method, and from hard bridge method it's 2.82302, whereas using the linear relationship 1.369383. So it's very low, but it could be because it's a theoretical relationship, and I don't have any other explanation for that. And here is the conclusion. So in this study, the thermal properties of flow sheets were measured using transient hard bridge method.